Okay, so there was a small thing left from last time, which was to basically argue that on an arbitrary curve, so when we had this Lagrangian, right? We had these two different Lagrangians. One which was, sorry, where did it go? Yeah, one which was this Lagrangian, which was the original Lagrangian that we started with, which is really sort of the path length that you travel along an arbitrary curve. And we're arguing that this path length is extremized, right? And the extremization of this path length gives you basically just the geodesic equation. Okay, and the geodesic equation, originally we had derived it by requiring that it's the straightest possible path. Okay, so on a metric space, what we found is the straightest possible path and the extremum path between 2 points on the manifold is the same. Okay, so geodesics do two things. They're not only the straightest path on a metric space, but they also extremize the arc length. And the way we showed this proof is, instead of taking this Lagrangian, we transformed the problem to a different problem by switching to this Lagrangian f, okay, which was like the square of that Lagrangian. Okay, so it was like L square by 2. And what we argued is that if you choose the parameter, okay, so here you had the freedom to choose a parameter lambda, and we said that if you choose this parameter lambda to be the arc length, okay, under this special case, okay, so now this Lagrangian in general, you are free to choose any parameter that you want. Okay, you can actually choose any parameter that you want for this Lagrangian, but under the condition that you choose it to be the arc length, okay, what we argued is that this second Lagrangian, which is f, okay, which is the square of the original Lagrangian, that also gives you the same equations of motion, okay, as the original Lagrangian. Okay, that is the equations of motion for f will be true if the equations of motion for L are true. Okay, but this was the very important condition that we required, was that the parameter that we're using, okay, must be the arc length. Okay, and so one important thing that we argued is that in this dl by d lambda is 0. That is, if you take the original Lagrangian, which was this one, okay, this doesn't change as I move along the curve, okay, or as I change my parameter lambda, which is my position on the curve, where lambda describes the arc length. Okay, and and this is actually so this we didn't basically argue why this is true. Okay, but actually, I mean, sorry, sort of, this was kind of obvious. Okay, so what you really had was sorry. Okay, so I'm not sure if we proved it. So what I wanted to argue was, so this quantity here is the norm of the tangent vector to the curve. Okay, and this is an arbitrary curve, and if I parallelly transport the this is an arbitrary curve, not a geodesic. Okay, it's only when we extremize the curve that we will get the geodesic. What I wanted to argue is that if you choose the arc length, this parameter lambda to be the arc length, then this is a constant. Okay, and you can set this constant to 1. And roughly the way I wanted to argue this is g mu nu dx nu is the arc length, and d lambda is the arc length. So okay, so this is roughly what I wanted to argue is this is the reason why this L is 1 along the curve. Okay, if you choose lambda to be the arc length. Not quite sure how to make this rigorous. Okay. I mean, hand wavingly, right? You just put the d lambdas inside. How to make that regress? Not quite sure. Okay. The other sort of interesting thing is that the original Lagrangian has what is called reparameterization invariance. Okay, that is, you're free to choose any parameter lambda. It doesn't have to be the arc length. Okay, but for the second Lagrangian, f, this f over here, you have to choose the parameter to be the arc length. You don't have that freedom anymore to choose any parameterization for the curve. Okay. And that constraint can be implemented by using a Lagrange multiplier. Okay, so maybe I'll give that as a homework exercise to sort of show this more thorough connection between these two. Okay, and ultimately what we did was we, instead of extremizing L, we extremized F, since we argued they have the same equations of motion. And when we extremized F, we ended up finding the geodesic equation with the same metric connection. Okay, this is Christoffel symbol using the torsion-free metric connection that we derived earlier. Okay. Okay, so so today what we're going to do is we're going to move on. This is probably the most important part now of we've been building up to this for a while, and now we're going to talk about the notion of curvature. Okay, and we're going to try to define what we mean by curvature on a manifold. Okay, so what we'll do first is we'll take our intuitive notions of curvature. Okay, then what we'll try to do is we'll see how those can be adapted, okay, to work for arbitrary manifolds. So let's think about our intuitive notion for curvature. So if we take a manifold like R2, just a plane, a sheet of paper, okay, with a flat metric. Okay, so this is your typical assumption of what flat space looks like, right? A two-dimensional space. You would say that it doesn't have any curvature. Okay, or if we had to quantify the curvature in some way, you'd say that that curvature is zero. Okay, we'll see what we mean by quantifying the curvature, but okay, you'd say that it has no curvature. Okay, this is flat. On the other hand, if you have a two-sphere like this, okay, which is embedded in 3 dimensions, like a ball, okay, the surface of a ball, you'd say that, so this is with the natural metric, okay, so now we know how to talk about this. So S2 is S2 with the metric inherited from R3, okay, so you embed this in R3 and look at the metric. And now this two-dimensional sphere, okay, it has a curvature, okay, and you'd like a way to quantify that curvature. Okay, so one notion that mathematicians used is something called extrinsic curvature. So you think about the fact that this is embedded in 3 dimensions. Okay, this is embedded in 3 dimensions. And now what you can do is you look at a point here on the sphere. Okay, and you can look at the center of the sphere and say, okay, in this direction, okay, if I move along the equator, it has a radius of curvature which is r. Okay, which is this radius. And if I move in this direction, okay, it also has a radius of curvature which is r. Okay, so what you do is you multiply the radius of curvature sort of in one direction and the other direction. Okay, so this only works in 2 dimensions, but you can use this to define a notion of curvature. And so for the sphere, the curvature would be 1 by r square. Okay, and the curvature, this is a completely homogeneous object, okay, homogeneous isotropic. So every it's a homogeneous object, so which means that every point on the sphere is identical to every other point in some way, right? So they're all related by symmetry. So the curvature actually at every point is 1 by r square. Okay, and mathematicians define this to have a positive curvature. Okay, so you can imagine that this is some kind of measure of curvature. Okay, it's you talk about the curvature as though it's kind of embedded in 3 dimensions, and you use the radius of curvature, okay, along different directions on this sphere, and you can define something like this. Now, this notion actually generalizes, right? This notion actually works even if you don't have a sphere, even if you have something that's not symmetric. You can kind of look at some kind of irregular 2D shape, 2D surface, right? And you can imagine that I look in one direction and then I look in sort of another direction, and I can imagine that if this is some arc, right? Sorry. If this is some arc, right, I can draw some arc, and I can ask, okay, where is the center? Okay, if there was a circle, where would the center of this circle be? And similarly, I can draw an arc, let's say in the perpendicular direction, and ask where the center of that circle would be. So there would be two centers, okay, which are, let's say, at radius r1 and r2, and then I could multiply the inverses of those and get a generic curvature. Okay, this is a generic prescription, okay, that you can use to define the notion of curvature when some object is embedded in higher dimensions. Now, you can apply a similar idea to a more complicated shape like this. Okay, so this is what is called a saddle. Okay, it's really like a saddle that you put on the back of a horse, right? So imagine that this is a horse and you're sitting on it, right? This is arched like this because the back of the horse is sort of arched like that, and your legs come down on either side. Okay, so the saddle also comes down like this. Okay, and yeah, so it looks like this. Okay, so this is a 2D shape. So over here you can see that it's curved. If I go along it this way, it's curved like this. If I go along it this way, it's curved like this. Okay, so depending on which direction I traverse the saddle at this point, right, the curvature would be this way, okay, and this way. So the curvature is kind of in some sense in opposite directions. So when I multiply these curvatures, they could be the same or they could be different numbers, r1 and r2. For one, I will use a negative sign. Okay, so let's say one is negative 1 by r1 and the other is positive 1 by r2. Okay, so we'd say that a saddle point like this has negative curvature. Okay, it has a curvature of minus 1 by r square. Okay, so this is a notion of negative curvature. Okay, so of course these definitions are sort of hand wavy. Okay, and we're not going to really make them precise here, but you can imagine that this is some way you could use to define curvature. Now, similarly, you could imagine why flat space has zero curvature. Okay, if I define a sphere, okay, with radius of curvature, sorry, the curvature is 1 by r square. If I take the size of the sphere to infinity, so you imagine the sphere becomes very, very, very large, then approximately when I'm on the surface, it's roughly flat. Okay, and therefore this curvature of a very large sphere goes to 0, which is exactly like flat space. Okay, so that's why we define flat space to have zero curvature. Now, the other thing, interesting thing about curvature is that it's a local property. It's not a property of the whole sphere. It's a property of a point on the sphere. Okay, it's a local property. It's not a property of the entire sphere. Okay, and different points. Okay, as I told you, different points on a two-dimensional surface or higher dimensional surface. You can imagine that you have a notion of curvature which is defined locally. Okay, at that point, what is the curvature? At a different point, the curvature may be something else. Okay, and the curvature can be both positive and it can be negative. Okay, so you can have positive curvature, negative curvature, zero curvature, and the curvature can vary at different points on the surface. Okay, and this is probably the most important point, is that curvature is a local property. Okay, it's not a property of the. So the sphere is symmetric, and that's why every point has exactly the same curvature. And so you might be fooled into thinking it's a global property, right? But if I have an irregular shape, right, I can define curvature sort of at different points, and those curvatures can all be different. Okay. Okay. Any questions here?
There's no way to sort of like make this definition embedding independent, right? So for example, I mean, S2 could be embedded either as a sphere, which is very normal, or you could also embed it as a ellipsoid in, I mean, just by scaling the axis unequally sort of, and then you would get a completely different curvature at basically the same point.
Yeah, so we did what is called an isometric embedding here, right? Basically, when you embed in 3 dimensions, you're taking the metric of 3 dimensions in your embedding and inheriting that metric on the sphere. Okay, so that is the distances between these 2 points on the sphere are the same as the distances as if they were embedded in 3 dimensions. Okay, if you had an ellipsoid, okay, you could imagine directly taking the ellipsoid as a 2D object embedded in 3 dimensions, and this can also be an isometric embedding. Okay, or I could get it from taking a sphere and non-isometrically embedding it. So like I kind of squash the sphere and stretch it as I embed it. Okay, in high dimensions. But but you can imagine just taking this ellipsoid with what is called an isometric embedding in 3 dimensions. That is, you preserve the distances on the ellipse from what they are by embedding in 3 dimensions. And then you can obviously see that the radius of curvature, right, would not be constant on this ellipse. So this curvature would not be a constant on the ellipse.
Yes, sir.
Okay. Other questions? Okay, so what we would really like to do, and this is consistent with the philosophy that we've adopted till now, we would really like to think about properties, all properties of manifolds independently of any embedding. Okay, and of course it would be nice if these properties relate in some way to this intuitive notion of curvature from embedding, right? But we would really like a definition of curvature which doesn't rely on embedding. Okay, we would like an intrinsic notion of curvature. Okay, so in other words, we're asking the question. Okay, for the specific version of this question is, how would ants learn that the Earth is round? Right. So we know that the Earth is round. Let's say because you have rocket ships. You go outside. Okay, so you see that we're actually 2D embedded in 3 dimensions, and you learn from the extrinsic curvature that, let's say, the Earth is curved. But if you were just confined to the surface of the Earth, as in fact we were for many thousands of years, right? How would you actually learn that the Earth is curved? Let's say even things like, let's say, observing stars and so on, right? That really relies on the fact that you're embedded in 3 dimensions. Okay, but let's suppose you can't look up, you can only look at things on the surface of the Earth, right? Or just at your eye level, right? How would you tell that you are on a curved surface? Okay, and the idea is as follows. Okay, we use the concept of parallel transport. Okay, once you have a notion of parallel transport, you can talk about curvature. So let's see how to define this. So let's consider flat space. Okay, so what we've already defined as flat space is this R2. Okay, with standard Euclidean metric, there's no curvature. Now, if I have a vector here at some location A and another vector here at some location C. Okay, let me parallelly transport these vectors. So initially these two vectors are parallel to each other. Okay, there are different points. Okay, but they're parallel to each other. How do I know they're parallel? Well, I can parallelly transport the vector from C to A, compare them, and I can see that they are the same vector. So it is parallelly transported, right? So the vector here is parallelly transported when I move it to A. Okay, there is no change in the vector, and therefore these two vectors are parallel. Okay, and of course this agrees with your intuitive notion of what is parallel from high school. You didn't need to do this course to understand this, right? So that is parallel. And now what you can do is you can parallelly transport these two parallel vectors, okay, which are slightly displaced from each other. So you can move this vector to B, okay, and you can move this vector to D. Okay, so you can move C to D and you can move A to B. And what you find is that again at their new locations, after moving them along a geodesic, okay, along a straight line, okay, these two vectors are still parallel to each other. Okay, so this is like one of Euclid's theorems in geometry, right? Is initially, or axioms, right? Initially parallel vectors remain parallel under parallel transport. Okay. So this is completely what you would expect in Euclidean space, okay, in flat space where there's no curvature, parallel vectors remain parallel. Okay, there are many ways to just say exactly the same thing that we just said. So this is one way to define curvature, but there are many equivalent ways of saying exactly the same thing. Okay, so we'll look at those different ways of saying exactly the same thing. So one other way of saying this is, instead of thinking about it as, let's take two initially parallel vectors, okay, which required us to compare two vectors at A and C, and parallelly transport them to B and D and then compare them again. Okay. Instead of doing that, what we could do is we could imagine that we just take C to D, then we take it from D to B, and then we take it from B to A, and then we bring it back to C. Okay, and then we compare it, okay, with the original vector that we started with. So basically we travel around a loop, okay, and we parallelly transport a vector around a loop, okay, and when we bring it back, what we find is that the vector is unchanged. So this is another way in which we can talk about space being flat. Okay, if parallel transport of a vector around a closed loop keeps the vector unchanged, then we say that the space is flat. Okay, and this would be true for any vector. Okay, and it would be true for any loop that we choose. Okay, the parallel transport of the vector around a closed loop keeps the vector unchanged. So it's not dependent on any particular vector or any particular loop. Okay, this is a general statement. Okay, if this is true for all vectors and all loops, then we have flat space. Okay, and another way of saying exactly the same thing is initially parallel geodesics. Okay, so what is a parallel geodesic? Well, it's if I take this vector and parallelly transport it to itself, right? That gives me a geodesic. Okay, because these are tangent vectors along a curve which stay the same. Okay, so this is a geodesic. And this is another geodesic which is parallel to that geodesic. How do I know it's parallel? Because the tangent vectors are parallel. Okay, so at some point these geodesics are parallel to each other. Now what I find is that if I look at some other point along the geodesic, these geodesics are still parallel to each other. That is, the tangent vectors remain parallel. So this is another way of saying this is a notion of no curvature in flat space. Okay, initially parallel geodesics remain parallel to each other at all times. That is, parallel lines remain parallel. Okay, this is probably more in line with Euclid's original version of the postulate. Parallel lines remain parallel. Okay, always. Or now, finally, if we come back to the way we had phrased the question very simply, right? If you have two ants which are walking in straight lines, okay, the straight line is the geodesic. If you have two ants on this walking on a straight line on a sheet of paper, okay, if the sheet of paper is infinite and it's flat, right, then they will never bump into each other, right? These ants will just keep walking in straight lines, and they will always see that they're just parallel to each other. Okay, they're neither getting closer together nor are they going apart from each other. Okay, they're still maintaining this sort of the same distance from each other. Okay, so they remain parallel to each other at all times. So these are equivalent ways of saying the same thing about parallel transport and its relationship to the flatness of space. Okay, and now we'll see that this notion, all these notions, okay, of parallel transport, okay, which seem obvious, okay, all these rules, okay, of parallel lines remaining parallel, okay, or initially parallel vectors remaining parallel under parallel transport, or parallel transport of a vector around a closed loop keeping the vector unchanged. All of these things fail to hold on a curved space. Okay, all of these properties fail to hold on a curved space. So let's see intuitively how that would be true. Okay, so again, let's look at this example of a 2D sphere. So what I've done, so imagine that this is the surface of the Earth, okay? And what we can do is imagine you and two friends, okay, A, B, C, okay? So this is you and two friends. And basically what you do is you stand parallelly to each other, okay? So you say that, okay, how do you stand parallelly? Well, you come close together. So A and B are right next to each other, okay? And you say, well, we are both going to walk this way, okay? This way meaning, okay, you pick a particular direction and say we're going to walk this way. Since you're at the same point, you're clear about what that direction is. Now your friend, okay, at B moves along some curve, okay, so he moves a little bit away from you. He doesn't want to bump into you when he's walking, so he just moves a little bit away. But he has to preserve his notion of parallel to you, okay? So he preserves his notion of parallel to you. So he has some notion of what it means to be parallel to you. So you are still here. Your friend moves a little distance away, but he has a notion of how to maintain parallel direction or a parallel vector to you. Okay. So now your friend is over here. Okay, and then your friend says, okay, I'm also going to walk in the same direction. You and me will keep walking in the same direction, and we'll keep following geodesics. Okay, so that is, as we move, we will keep our vectors parallel to whatever direction we started with. Okay, so if we started moving in one direction, we'll try to move on the straightest possible line. That is, our velocity vectors or our tangent vectors will remain in the same, will remain unchanged relative to our old velocity vectors. Okay, so that's what we mean by parallel transport. And so I've shown two friends here, A and B, and let's say you have one friend is a bit lazy, so he stays relatively close by, doesn't go very far. and the other friend is more adventurous, so he goes halfway around the Earth, okay, or quarter way around the Earth, around the equator, okay, to point C. But you can see that all of these guys, right, were basically parallel to each other, right? I mean, if you bring them together along the equator, they will all agree that they're moving parallelly to each other. Okay. Now, let's see what happens, okay, as they start moving. Okay, so let's imagine that they follow their geodesic. So A moves, okay, and as A moves here, this vector is parallel to the vector that he started with. As B moves, she sees that her vector is, let's say, parallel to the vector that she started with. And as C moves, she sees that this is the vector, okay, the tangent vector that is parallel to the direction that C started with. And so they can continue doing this. Okay, so A keeps moving parallelly to whatever direction he was previously moving. B moves parallelly to the direction she was previously moving, and C moves parallelly to the direction he was previously moving. And so finally, what would happen is if they walk far enough, right, they would find that they all bump into each other at the North Pole. Okay, or at least they all pass the North Pole at some point. Okay, maybe they're walking at different speeds. Okay, but they will all pass the North Pole. Okay, and at the North Pole, okay, let's say they stop, okay, and then they compare their velocity vectors. A's velocity vector is going that way, right? A is going to come around and go around on the other side of the Earth. B is going this way, okay? B is also going to come around and go on the other side of the Earth, okay? And to see it more clearly, if you look at C, C is coming around this way, and C is now going this way, okay? So C is going to come down and go this way, okay? So the first thing you do, okay, is you look at your friends B and C, okay, and imagine that this was, pre-Copernicus, right, or pre, whenever you think people thought the Earth was flat, right, and A, B, and C, you're saying you all meet, okay, and then you're like, I was going straight, you were parallel to me, and you were supposed to be going straight, okay, yet now that we're here at the same point again, which is this point, okay. Why is it that you are going in a different direction and I am going in a different direction, right? We should be parallel to each other. That's what you think. So, and this is how you realize that you're on a curved surface. Okay, this is how you realize you're on a curved surface, is because initially parallel vectors fail to remain parallel as you parallelly transport them. Okay, so as you parallelly transport these vectors, they fail to remain parallel to each other. Okay, and this is okay. So this is true not just for the velocity vector, but you could imagine that A and B are carrying, let's say, an arrow with them. Okay, so they're carrying an arrow which is pointing in a different direction. So A and B are carrying arrows like this. Okay, and A parallelly transports his arrow. Okay, B parallelly transports her arrow. Okay, and C parallelly transports his arrow. Again, these three arrows, okay, even though they were parallel on the equator, right, along the A, B, and C thought they were parallel to each other. When they meet at the North Pole, those three vectors are not parallel to each other. So initially, parallel vectors fail to remain parallel, okay, when you transport them, okay. So this is kind of a diagnostic that you can use now to figure out that you are on a curved surface without reference. Without ever getting off the surface, right? Without ever realizing that you're embedded in some higher dimensions, right? You'd find that initially parallel vectors just fail to remain parallel. Okay, that's how you can tell that you live on a curved space. Okay, another way to say this is geodesics fail to remain parallel. Okay, this is obvious from our discussion above, right? If I use the tangent vectors being parallelly transported or unchanged, right, that basically gives me a geodesic. Okay, and these geodesics, okay, which are, let's say, longitudes in this case, okay, they all converge. Okay, versus in flat space, the geodesics, which are straight lines, they don't meet. Okay, parallel lines remain parallel forever. Here, geodesics fail to remain parallel. Okay, or geodesics converge in this case. Okay, or if I'm going in the opposite direction, geodesics diverge. Okay, so they either converge or diverge. Basically, they fail to remain parallel to each other. Okay, and now to say this colloquially, right, in terms of the ants, right, any ants which were walking on parallel straight lines initially parallel straight lines, they will end up bumping into each other. Okay, so they will get closer to each other, or their paths will converge, and that's how the ants would realize that they, if they're smart enough, that they lived on a closed, on a curved surface. Okay, and finally, the other way of saying it is as I go around a loop. Okay, so imagine that I'm here at A. I have this vector and I parallelly transport it with me. So as I go from A to B, I parallelly transport it, and now it's pointing that way. So it's pointing into the page. Then as I move along this path, okay, to the North Pole, I parallelly transport it, and now it's still pointing into the page. And now I come from C to D and I parallelly transport it. So I would do this, right? And now when I come back to A, okay, this vector is no longer pointing along the original direction, right? It's pointing this way. It's pointing towards the North Pole rather than pointing along the equator. Okay, so a vector which is parallelly transported around a closed loop. Okay, this is a closed loop on the surface. It does not come back to itself. Okay, it in general, this vector when I come back to this point does not agree with the vector that I started with, even though I was parallelly transporting throughout. Okay, so this is a way that you can use to diagnose that you live on a curved surface. Okay. Uh, so all those different ways of saying that you live in flat space, okay, initially parallel vectors remain parallel under parallel transport. This fails, okay, on a curved surface. Okay, parallel vectors do not remain parallel. Parallel transport of a vector around a closed loop keeps the vector unchanged. This fails. As you go around a loop, the vector can change directions. Initially, parallel geodesics remain parallel to each other at all times. That is, parallel lines remain parallel. That's not true. Longitudes converge. Okay. Ants walking along initially parallel straight lines never bump into each other, neither getting closer together nor further apart. The ants will eventually bump into each other, even though they think that they're moving parallelly to each other. Okay. So that is how you will realize that you are living in curved space. Okay. Is this idea clear? Any questions here?
Sir,
Yeah.
regarding the second point, the vectors in a closed loop do not preserve the direction. If it's a geodesic, then the tangent vectors will remain in that direction only, no, sir? If the closed loop is a geodesic.
Yes, you're right. So this is not true for all vectors. Some vectors parallelly transported around a closed loop will not come back to themselves. Okay, so this is true in general. So what you said is absolutely right. So if I go around a geodesic, right, then as we know, so for example, this is a longitude, right? So as I go around a longitude, by definition, right, it's a geodesic, and therefore the vector will come back to itself. Okay. So it's not true that every vector parallelly transported around a closed loop will not does not come back to itself. As long as some vector around some loop parallelly transported does not come back to itself, that is sufficient to tell you that the space is curved. That's a good question. Okay, we'll see. In fact, that the other important property is that we want curvature to be a local property. Okay, so we'll see how that. In fact, we're going to try to use this notion of curvature, even though all these notions are sort of equivalent, right? We'll use this notion of curvature. Okay, some vector parallelly transported around some closed loop does not come back to itself. Okay. The other thing that we'll want to do is make this property a local property, that is a property of a point rather than a property of the loop. Okay, and also just to continue this example, on a negatively curved space, okay, again you can see that, you know, if I'm not going to do all the examples, but if you imagine that two paths which are parallel, right, they will start diverging as I go outwards on this saddle. Okay, one will start going off on one side of the saddle, one will start going the other side, and they'll diverge. Okay. So what we'd like to do is we'd like to formalize, okay, this notion of curvature, this notion of curvature through parallel transport. Okay, we'd like to build up this notion of curvature as something that is intrinsic to a manifold with parallel transport defined on it. So you see that it's not sufficient just to have a manifold. You also need to have a manifold with parallel transport defined on it. That parallel transport may or may not be associated with a particular metric. Okay, but you still need to have the notion of parallel transport defined. Okay, this notion of curvature that we will define through this parallel transport, this will not rely on any embedding. Okay, this will not care whether the S2 lives in R3 or you embed it in some higher dimensions, or even if no such embedding exists, you will still have a notion of curvature which doesn't rely on that embedding. You don't have to leave the manifold to realize that it's curved. Within the manifold itself, you have a way to diagnose whether the manifold is curved. Okay, so that's really the interesting, powerful aspect of this notion of curvature. Okay. Okay, so now let me just tell you some points to note before we move on. So curvature can be defined on any manifold, okay, which has a connection. Okay, it just needs a connection which allows you to do parallel transport. Okay, so it doesn't have to be a metric on the manifold. Okay, as long as there's a connection, or equivalently, instead of talking about gamma, you can talk about this affine connection delta, right? Because we defined these gammas so that we could define a connection. This was sort of a coordinate dependent way of describing parallel transport. Delta sort of gives you a coordinate independent way of describing parallel transport. Okay, it's an operation which takes you from two vectors to a scalar. Okay, and if you can define such a notion or define such an operator, then you've defined the notion of parallel transport. Okay, so the connection that we're talking about here, this gamma, right, or even the gamma that shows up in delta, okay, this need not be a metric connection, okay, and the manifold need not even have a metric. Okay, that's an important point. It really is. I mean, even though in GR we will be working only with metric connections, okay, and torsion-free metric connections. In general, it's good to remember this, okay, that it need not be a metric connection. Okay, you just need a notion of parallel transport. And so, of course, if the manifold has a metric, okay, if the manifold has a metric like the metrics that we'll see in GR, okay, then you have a unique torsion-free metric connection, which is the Christoffel symbol, and the curvature can be defined through this particular connection. Okay, this metric compatible connection. Okay, this is the connection that ensures that dot products of vectors v dot w, where this v dot w is defined through the metric G. Okay, this quantity is zero under parallel transport. Okay, or the change in scalar products don't change. Okay, scalar products of two vectors don't change under parallel transport. Okay, that is that defines parallel transport, which is metric compatible. Okay, so with this particular choice of a metric compatible connection, okay, you have some notion of curvature that you can come up with. Okay. Okay. The other thing that we'd like is that the notion of curvature, whatever notion of curvature we define, it should be local. Okay, it should be defined at each point on the manifold. It should not depend on the whole manifold. You can measure curvature locally at individual points of the manifold. Okay, because we've seen that curvature is a local property, right? And we'd like to define it in such a way. Okay, so what we will show, okay, is that rather than quantifying the curvature by a single number at every point, okay, like we did this 1 by R1, R2, okay, rather than quantifying it by a single number at every point on the manifold, it will be quantified by a tensor field, okay, and it will turn out to be a 1,3 type tensor field. This seems rather strange. Why is it a 1-3 type tensor field? We'll see that this is quite a natural notion given our definition of parallel transport. Okay, but let me just say what exactly this. Sorry, we should really write this. Okay, so there'll be some tensor. Okay, and this tensor is called a Riemann curvature tensor. Okay, so it's a tensor, which means that it exists independently of any coordinates that you put on the manifold, right? Like we've seen vectors, dual vectors, tensors, they all exist independently of any coordinates that you put on the manifold. However, in a particular coordinate system, you can write down the tensors with some basis coefficients. Okay, so these are those basis coefficients, and it's a type 1-3 tensor, which means I expand it in a basis which involves one vector, okay, and 3 dual vector type indices. Okay, and this is a coefficient r sigma rho mu nu. Okay, and this, if it's a tensor, okay, it must satisfy a tensor transformation law. Okay, which means if I switch my coordinate system, these coefficients r must transform like a 1-3 tensor. Okay, I'll write that rule for a 1-3 tensor and how it transforms somewhere later in the class. But that's an important point. Okay, this is a tensor. It's not just a collection of these numbers, right? It really has to transform like a tensor so that it is defined in a way that doesn't rely on any particular coordinate system. Okay, the tensor exists independently of any coordinate system. What we'll see is that this tensor, okay, r sigma mu nu rho, okay, or these tensor coefficients rather, okay, roughly speaking, I can write them using gamma, and gamma, you remember, was a basis dependent connection coefficient. Okay, so something like this. We'll roughly see that it depends on derivatives of gamma and some squares of these gammas, okay, appropriate with indices appropriately contracted. Okay, so this curvature tensor will be defined in terms of the connection gamma, and gamma itself, we've seen, does not transform like a tensor. Okay, gamma itself does not transform like a tensor, but this particular combination, okay, when you take all of these things in some particular combination, it ends up transforming like a tensor, and it captures all of those properties that we were talking about failure of vectors when parallelly transported around a closed loop to remain parallel. Okay, this curvature tensor captures those effects. Okay, so we'll see how it does that. So the Riemann curvature does transform like a tensor, even though gamma itself does not transform like a tensor. Okay, therefore gamma itself, okay, doesn't really have a geometric meaning. Okay, because gamma you have to specify in some coordinate systems and so on. Again, delta, okay, this affine connection, you don't have to use a particular coordinate system to specify its meaning. Okay, so similarly, this r sigma mu nu, or sorry, not this, the Riemann curvature tensor, okay, which of course I can expand in some basis. The tensor itself has a meaning, a geometric meaning, which means it's associated with the manifold. It's a particular 1-3 tensor, okay, that you're associating with this manifold. So that particular 1-3 tensor then describes the curvature of this manifold. Okay, it is a tensor field because it's defined at every point on the manifold. So if at some point on the manifold, I want to know what is the curvature tensor. Okay, so I evaluate what is the Riemann tensor, this Riemann tensor, or I'll evaluate those coefficients, and I'll evaluate them at some particular point P on the manifold. Okay, so it'll return some numbers for me. Those numbers in some way quantify the curvature. Okay, what do those numbers mean? Well, we're going to see what they mean. Okay. So now what we're going to do is we're going to construct this idea of a Riemann tensor to capture those intuitive notions of curvature that I just described to you. Okay, so imagine that this is a manifold. Okay, so this is some part of a manifold, and these are some coordinates. Okay, so this is so I'm starting here at a point P, and the point P has coordinates x mu. Okay, we'll do this initially in a particular coordinate system. Okay, and then we'll later show that the Riemann tensor that we define is actually coordinate independent. So let's say we start here at point P on the manifold. Okay, these 4 lines that I've shown, this kind of hash, this one, and this one, and this one. Okay, they represent displacements. Okay, so there's no notion of distance, just displacement on a manifold. So as I change my x mu coordinate to x mu plus some epsilon mu, okay, that is, as I add an amount epsilon mu to my coordinate, I move from the point P to the point Q. Okay, this point S corresponds to a different displacement, okay, in a different direction. So as I add some other vector, okay, with coordinates delta mu to x mu, I move from the point P to the point S. Okay, so the coordinates of S are x mu plus delta mu. Okay, where I'm assuming that these epsilons and deltas are small. Okay, these are tiny displacements. Okay, so these epsilons and mu's are deltas are tiny displacements. And now we can construct a point R, okay, which involves a displacement by both epsilon mu and delta mu. Okay, and there are two ways in which I can think about traveling from P to R, okay, in this coordinate system. I can imagine traveling first by changing my epsilon by coordinate by an amount epsilon, and then changing it by an amount delta. Okay, or alternatively, I can think about first changing my coordinate by an amount delta, and then changing it by an amount epsilon. Okay, both of these approaches should take me to the same point, because a single coordinate should label single values of these coordinates should label a single point, okay, in a coordinate patch. Okay, we're assuming all of these fit into one coordinate patch. So therefore, the point R that you get is a unique point. Okay, but you can approach it from different paths. Okay, and these different paths are along some different epsilon and delta directions. Okay, so we'll define these two paths. One shown in pink over here. This is path 1, which is first I travel by making an epsilon displacement, then I make a delta displacement. So epsilon is roughly this way, delta is roughly this way. Okay, and again epsilon is this way, delta is this way. Okay, so path 1 I first displace by epsilon, then I displace by delta. Path 2 is first displaced by delta, and then I displace by epsilon. Okay, so the C prime shows the second path, and this path C, which is in magenta, okay, that shows the first path. Okay, so these are two different ways that I can go from P to this point R. Okay, and now along this path from P to R, okay, I look at what is, if I have a vector V naught at the point P. So I have this vector V naught at the point P, and now I parallelly transport it along the curve C. Okay, I parallelly transport it along one path, it is C. So as I parallelly transport it along C and I come to R, I will get a vector which corresponds to a parallelly transported version of V naught, okay, which was moved. So as I move it from here to here, I get the parallelly transported version at the point Q. As I move it from here to here, I now get the parallelly transported version at the point R, but this depends on the curve C that I took to get here. Okay. Now I could have done the same thing by parallelly transporting this vector V naught along this direction. So first I transport along the delta, and I get some Vc prime at the point S. Okay, so this is the parallelly transported version of this curve along C prime at the point S. Then I transport from here to here, that is I transport by epsilon. So now this gives me some Vc prime at point R. Okay, so this is another vector. Okay, and the important point is that in a curved space, these two vectors may not agree with each other after parallel transport. Okay, so parallel transport along C prime will give me this vector Vc prime R, okay, which now belongs to the tangent space at R. And this gives me another vector VCR when I parallelly transport it along C. And these two vectors may not agree with each other, even though they are two vectors in the same tangent space. And these two vectors came from parallel transport of the same vector, but along different paths. Okay, so parallel transport of a vector along different paths may not give you the same vector. Okay, so what we're interested in is the difference between these two vectors. Okay, if these two vectors have a non-zero difference, then we'll say that the space is curved. Okay, then we'll say that the space is curved. The other important point, so we want to construct this difference vector. What is the difference between those two vectors, which were parallel transports of the same original vector V naught, okay, at the point R? And if this difference is non-zero for arbitrary infinitesimal paths, okay, these infinitesimal paths are parameterized by these deltas and epsilons. So for arbitrary choices of these displacements delta and epsilon, and for arbitrary vectors, okay, if some or some particular choice of sorry, rather than arbitrary, some infinitesimal path rather than arbitrary, so some infinitesimal path and some vector, okay, doesn't matter which vector and which path, as long as this happens for some choice of vectors and some infinitesimal path, that these two are not the same, okay, then we conclude that the point P has non-zero curvature. Okay, so then you conclude that this point P has non-zero curvature. Why do we associate this curvature with the point P? Well, basically that's the entire reason why we're taking infinitesimal paths. If the path is infinitesimal enough, right, what we'll see is that there is a notion of curvature that you can define that doesn't really depend on the displacement. Okay, it doesn't really care about this displacement in the limit that that displacement goes to zero. Okay, in the limit of these displacement vectors going to zero, there is a notion of curvature or the difference between these two things. Okay, which will still survive. Okay. Okay. Any questions here? Okay. So let's construct these two vectors, okay, in our coordinate system. Okay, so let's construct the vector Vc prime r and let's construct the vector Vcr, remembering that these are parallel transports of V0. Okay, and as an intermediate step, so let's imagine that we're going along the path C prime. Okay, as an intermediate step, we'll first construct the vector. We have to construct a Vc prime r. So we'll work our way backwards. Okay, so we'll write Vc prime r first in terms of Vc prime s. Okay. So to get from Vc prime s to Vc prime r, we have to parallelly transport along make a displacement epsilon. Okay, this way. So Vc prime. Okay, so now if I write it in coordinates, Vc prime at r, okay, is related to Vc prime at s through a parallel transport, which means if it's a parallel transport, it involves a connection. Okay, so it's gamma mu rho nu. It's proportional to the displacement in coordinates, it's proportional to this epsilon rho, and it's proportional to the vector v at the point s. Okay, so it's proportional to this vector v at the point s. Okay, where this is this vector over here. Okay, so this is straightforward enough. Okay, the other important point is that the Christoffel symbol that we're using, sorry, not the Christoffel symbol, the parallel transport coefficient that we're using. Okay, this is not necessarily a metric compatible connection. This is an arbitrary connection. This is evaluated at the point S. Okay, this is also the connection at the point S. Okay, because we're parallel transporting from S. And now what we can do is we can now take this vector. Okay, and this vector itself is obtained by parallelly transporting V0 from P to S. Okay, so now we can write that equation. So we can say that the vector at S, okay, which was obtained by traveling along the path C prime, is equal to V0 mu, okay, because that's the vector I started with at the point P. Again, parallel transport, but now this parallel transport coefficient is at the point P, okay, because that is the point over here from which I'm starting my displacement. Okay, so it's the parallel transport coefficient at the point P, gamma mu rho nu, and again I will have the displacement, okay, which is delta rho, and I will have the vector components, okay, that is V0 nu. So under parallel transport, okay, the vector components get sort of mixed up among themselves in a linear way, right? So under a small enough parallel transport, right, we argued that Vc prime mu of S should just be proportional to these original vector coefficients, okay, of V0 mu. Okay, okay, so now what we can do is we can plug this in here, okay, And we have VC prime at S appearing twice, once over here and once over here. And once we plug it in, what we will get is we will relate the final vector VC prime at R, okay, which is this vector. Okay, this is the parallelly transported version of the vector V naught, parallelly transported along the curve C prime. Okay, we will get that. Okay, we'll eliminate this intermediate vector. Okay, and we'll express it purely in terms of V naught. Okay, so we'll purely express it in terms of the original vector V naught and these connection coefficients. Okay, and these connection coefficients. Yeah. Okay, so let's do that. Okay, so we'll plug in for this VC prime S. Okay, as this entire expression. So when we do that, we'll of course get V naught mu minus gamma mu rho nu. So I'm keeping this. Okay, mu rho nu S V naught nu epsilon rho, and now I'll also have this term. Okay, coming from here. Okay, which is minus gamma mu rho nu, but this is at this connection coefficient is evaluated at P. Okay, times V naught nu times delta rho. Okay, that's what's showing up here. And now I'll have one more term. Okay, and this one more term will be quadratic. Okay, it'll have a product of delta and epsilon in it. Okay, because this is coming from taking this intermediate vector at S. Okay, VC prime at S, and now expanding that. Okay, in terms of all of this. And the one more thing that I have to do when expanding, I have to be very careful about indices. Here VC prime, I'm looking at the newth component. So I have to replace this with new. And when I do that, you need to be very careful. Okay, so let's write it out, okay, explicitly, so that it just helps you when you're doing this on your own. So when I write it in terms of this index new, okay, I'm just changing the dummy index on this side. Okay, I will have V naught new minus gamma new rho. Now you have to be careful. There's already a new over here. I don't want to use that index new again. So what I will do is I will use a different index. Let's say I use eta. Okay, and then if I use an index eta, then this is V naught eta delta rho. Okay, because now this new index is the free index, so it means something different. Okay, so I don't want, and this is a repeated index, so I can use any arbitrary other index for that repeated index. Okay, and this is at the point P. So now I plug this in, okay, over here, and what I get is so I have a minus gamma. Okay, and then when I plug this in, I will get a plus gamma square. Okay, so you'll get a plus gamma square type term. So let's write down exactly what that is. So this term will be, this part will be unchanged. This part will be unchanged. So I'll have, let me first write it here, and then I'll show you what I wrote in my final expression. Okay, so I'm plugging into this piece. Okay, so I'll have gamma mu rho nu S. I will have a minus sign times a minus sign, so a plus sign. I will have a VC prime of nu of S, which I'm going to replace with this. Okay, and I'll have an epsilon rho. So I'll have epsilon rho. And now I'm going to replace with this. Okay, and now I need to be careful. I've already used the dummy index rho. Okay, so I don't want to use the same dummy index rho over here. Okay, so what I'm going to do is I'm going to replace this dummy index rho by sigma. Okay, so now when I do this, I get a delta sigma. Okay, and then I get a gamma nu sigma eta p, and I get a v naught eta. Okay, so this is the extra term that I need to write down now. So I had one term, two term, and this is the third term. Okay, two gammas, v naught delta epsilon. So let's just check. Okay, so you can see that there is some slight difference in the labeling. Okay, so you should be able to do these comparisons on the fly, which is why I'm showing you how to do it. Okay, so you see that the mu is the free index. Okay, so the mu index is like kind of my anchor. Okay, so the mu index appears here, and now what we see is that I have a sigma and an eta index here. Okay, And here I have a mu index, but here I have a rho and a nu index. Okay, but these indices are repeated, so I can always change the labeling. Okay, so if I, instead of over here, what I can do is the rho index I can replace by sigma. Okay, so if I replace rho by sigma, I'll replace it here. Let me just write it out carefully. Okay, so the changes I want to make is I want to replace rho by sigma, and I want to replace nu by eta. Okay, and then if I look at the next term, I have a gamma, and now this will be an eta. Okay, which is good because that's what I have here, gamma eta. And now I want to replace this sigma by rho, and I want to replace this eta by nu. Okay, so you can see that these two gammas will become this when I make these replacements. Okay, but what about the remaining stuff? So V naught eta becomes V naught nu, which is what I have here. Epsilon rho becomes epsilon sigma, which is what I have here. And delta sigma becomes delta rho, okay, which is what I have here. Okay, so you should get very, very comfortable with this kind of index notation, okay, changing of indices, and most importantly, making sure that your repeated indices, okay, lower mu, upper mu, this only appears once. Okay, if it appears more than once, you made a mistake. You put in the indices too many times. You use the same index, the same letter for the index. Okay, so you're going to get confused. Okay, so you should get very comfortable by practicing this if you're not already familiar with it enough from special relativity. Okay. Okay. So now. Okay. So now that we have this. So this tells us VC prime mu of R. It tells us the components of the vector here in terms of the original vector V naught. Okay, in terms of the original vector V naught. So V naught appears here, V naught appears here, V naught appears here, V naught appears here, of course. Okay, so it's two parallel transports. Okay, so it's not surprising that it appears with an epsilon and a delta. Okay, so there's an epsilon and a delta, both appear. Okay, and the other thing that you'll see is that these connection coefficients, one of them is evaluated at the point S, here and here, but another one is evaluated at the point P. Okay. So what we'd like to do is we'd like to relate the connection coefficient at S. So if I write the connection, some arbitrary connection coefficient, gamma mu rho nu at S. Okay, in terms of coordinates, it depends on the coordinate x mu plus delta mu, right, which was the coordinate of the point S. Okay, so this was S. This was the point S, and this had coordinates x mu plus delta mu. Okay. So if I think of it as a function of x mu plus delta mu, I can do a Taylor series expansion of this function, and I can write it as gamma mu rho nu of x mu plus I can now write it as a derivative. Okay, for a small enough delta mu, I can do this Taylor series expansion and write it as a derivative. So partial sigma, which is partial x sigma, gamma mu rho nu. Okay, the derivative evaluated at x mu. Okay, times that displacement delta mu, okay, which I write as delta sigma, okay, plus some higher order terms, which will be second order in the derivatives. Sorry, second order in delta. Okay, I won't write the second order terms, but there's order delta square. Yeah. Okay, and so now these x mu's, this is telling me that I need gamma at x mu, or I need the derivative of gamma at x mu. The point x mu corresponds to the point P. So now these gammas, I related the gamma at the point S to the gammas or the connections at the point P, okay, by this kind of Taylor expansion. Okay, so now we'll plug in this kind of Taylor expansion. So we'll plug it in here, okay, and we'll plug it in here. Okay, and at the end, we're going to keep things which are up to order epsilon times delta, or order delta square, or order epsilon square, but we won't go higher order than this. Okay, we'll only go up to this order. Okay, so for example, we won't keep things like order epsilon times delta square. We'll say that's too big order and that's too small. Okay, in these displacements, we'll assume epsilon and delta are of the same order. Okay, now when you do this, okay, so I'm going to plug in here. Okay, so what you get is you of course get gamma mu rho nu, okay, times V naught nu epsilon plus delta mu, plus delta rho. Sorry, I think I did some clubbing terms together. Yeah, so what I did was, so this particular term is evaluated at P plus there's a derivative of this evaluated at P. So I take the term which only involves this term evaluated at P, okay, and I club these two terms together. Okay, one of them has an epsilon rho, one of them has a delta rho. Okay, so I'm going to get a term like gamma mu rho nu, V naught nu, epsilon rho plus delta rho. Okay, the other term is going to be from this term with now the derivative expanded. Okay, so that's this first order term in the Taylor series. So it's going to be minus partial sigma gamma mu rho nu times V naught nu delta sigma, and now there's an epsilon rho, and that epsilon rho is coming from here. Okay, because I expanded this term in a Taylor series. So this is what I have. Okay, from the first. From these two terms, from this term and this term, I get this and this. Okay, and now my third term over here. In my third term, I only need to. So this, although this is gamma at S, when I do a Taylor series expansion, this will have an extra term which is like delta sigma. But this term multiplied by delta rho epsilon rho is higher order. It's third order in these infinitesimals. So really, I just need to keep this. I can just basically think of this as gamma evaluated at the point P. I can forget about the fact that this is evaluated at S. Okay, so I get gamma mu rho eta, gamma eta sigma nu, V naught nu epsilon rho delta sigma. Okay, plus now I have terms which are higher order in epsilons and deltas. Okay, I neglected all of those, and all the gammas and derivatives of gammas are evaluated at the point P now. In this expression, all the gammas are at point P. Even these derivatives of gamma, they are all evaluated at the point P. Okay. Okay. Any questions here? Is it hard to follow the math online, or is this making sense?
Sir, I think I'm following it. Also, it kind of reminds me of the question that you had asked us in our STR exam, which was basically the combination of a X boost, infinitesimal X boost, and a Y boost being a rotation around the Z axis.
Yeah, yeah. Well, the algebra is a bit similar. Yeah. Of course, this is not exactly that. What about the rest? I mean, just let me know, right? If it's too difficult to follow the math, or especially the indices, right? I really want all of you to have good practice with these indices because that's essential if you're going to calculate things in GR. Okay, so let me move on. Okay, so now we've basically calculated V mu C prime at R. That is, we've calculated. We started, let me say, so we started here, we parallelly transported like this, and now we calculated this vector. Okay, now what we'd like to do, okay, is similarly calculate as we move this way and then this way, what is this vector VC of R. Okay, and we don't have to repeat the work, right? We can be smart about it. So first we move by epsilon, first we move by delta and then we move by epsilon, and now we're moving first by epsilon and then moving by delta, right? Okay, so what we can do is in our expression over here, okay, for this, oops. Yeah, in our expression for VC mu prime of R, if we want to similarly evaluate now the transport of V, okay, or V naught as I move along the other path, that is along the curve C rather than along the curve C prime. Okay, what should we do differently? Okay, well, one thing is we can exchange the epsilons and deltas. Okay, we can exchange the epsilons and deltas. Right, so all we have to do is just exchange the epsilons and deltas. So when we exchange the epsilons and deltas, of course, this term stays unchanged. Okay, this term changes. Okay, so now it becomes, okay, sorry. So we can exchange the epsilons and deltas, but instead of exchanging the epsilons and deltas, we can exchange the indices on the epsilons and deltas also. Okay, because these are dummy indices, right? Every time the epsilon and a delta appears, whatever index it comes with is a dummy index, and that it's summed over. Okay, so what we can do is we can also, instead of exchanging epsilon and delta, we will both exchange epsilon and delta. So we'll change epsilon for delta and we'll change delta to epsilon. But we'll also change the dummy index on the epsilon to the dummy index on the delta. Okay, so if epsilon comes with a row index, we will change it so that after changing it to delta, it now becomes a delta with a dummy index of sigma. Okay, so rho becomes sigma. Okay, it's a dummy index, so it doesn't matter. Okay, and similarly, we will do the same thing for delta. So delta sigma, we'll change it to epsilon rho. Okay, so this is the change that we'll make. Now, what do we need to ensure? We need to ensure that every row that appears, okay, because rho will appear twice because it's once here and once in the epsilon, that row should also be changed to a sigma. Okay, so that it's clearly summed with the epsilon and not with something else. Okay, or sorry, now the epsilon itself has changed to a delta. Okay, so it should be summed with that delta. So when we do this, okay, what we will get is, so we write VC mu of R will be V naught mu minus, let me just zoom out a little. Okay, gamma rho mu rho nu. Okay, it's exactly the same term here, V naught nu. Okay, then there's epsilon rho plus delta rho. Okay, that is, here nothing has changed because epsilon and delta just got exchanged, but that keeps the term the same. But it will matter in these two terms, okay, in the next two terms. So here I have partial rho because I now exchange the rho and sigma labels. So gamma mu sigma nu, V naught nu, and now I still have epsilon rho and delta sigma. Okay, so effectively by this change, what I've done is only change the labels, okay, from rho to sigma and sigma to rho. Okay, but really what I've done is secretly I've interchanged epsilon and delta. Okay, that's what has actually happened. Okay. And similarly in the last term over here, okay, I have a gamma mu, again I replace rho by sigma, so sigma eta, and I have a gamma eta sigma nu, which is gamma rho, eta rho nu, and I now have V naught nu epsilon rho delta sigma, so V naught nu delta rho epsilon sigma. Okay, again I change the epsilon to delta. Sorry, no. This is still epsilon rho. I mean, this has become delta sigma epsilon rho. Okay, so it's still a delta sigma epsilon rho. Okay, okay, and now I want to evaluate the difference between these two vectors. Okay, so now I've evaluated these two vectors, and now I finally want to know what is the difference between these two vectors. What are these two vectors? They are different ways of parallelly transporting V naught. Okay, one gives me VC prime at R, one gives me VC of R. And if the space is curved, the difference between these two vectors is going to be non-zero. Okay, so I want to evaluate this difference. Okay, because that is going to be the diagnostic of curvature. So let's take the difference between the two. So you can see that this term, and this term, okay, they will cancel out. Okay, when I take the difference. So the difference between them will be proportional to this V naught nu. All these terms have V naught nu epsilon rho delta sigma, V naught nu epsilon rho delta sigma. Okay, so both terms have V naught nu epsilon rho delta sigma, V naught nu epsilon rho delta sigma. So the entire difference between them is just proportional to this V naught nu epsilon rho delta sigma. Okay, that's why we did that relabeling of indices. And now we just see the coefficients. Okay, so when I take minus of this, I get a plus sign accompanying this term. Okay, so I get a partial rho gamma mu sigma nu. Okay, I get this. And from here, I get minus partial sigma gamma mu rho nu. Okay, so I get minus partial sigma gamma mu rho nu. And now I get, from this term, I get plus gamma mu rho eta, gamma eta sigma nu. Okay, so gamma mu rho eta, gamma eta sigma nu. And from here I get a minus now because I'm subtracting this vector, minus gamma mu sigma eta, gamma eta rho nu, minus gamma mu sigma eta, gamma eta rho nu. Okay. And now everything inside this bracket we define as R mu nu rho sigma. Okay, because those are the free indices. There's an upper free index mu, their lower indices are nu rho sigma. So I can just define this object. Okay, so this is a definition, and so my difference between those vectors is v naught nu epsilon delta, epsilon rho delta sigma times R mu nu rho sigma. This is just right now I've just defined R mu nu rho sigma. It's just this thing. Okay, whatever is in this brackets here. Partial rho gamma mu sigma nu minus partial sigma gamma mu rho nu plus gamma mu rho eta gamma eta sigma nu minus gamma mu sigma eta gamma eta rho nu. Okay, this is just a definition right now. Okay, I've not shown that this is a tensor or anything like that, right? But this is just a way to define, relabel all those coefficients and put it into one symbol. Okay. Okay, so now I've got the difference between those two vectors. Okay, so let's first observe a couple of things about this difference. Okay, so the difference between these two vectors, okay, is proportional to epsilon and delta. Okay, it's first order in epsilon and it's first order in delta. Okay, so the difference between the vectors shrinks to zero size when the loop shrinks to zero size. If the loop shrunk to zero size, then there would be no difference between the vectors, right? Because basically you're just stuck at this point. You're never actually moving, so you're never actually transporting. Okay. So really, it's not the change in V that we should think about. Okay. We should think about the change in V per unit displacement area. Okay. Again, the notion of area itself is not defined, but we can think of a notion of how much is the displacement delta, how much is the displacement epsilon. And roughly speaking, we are in some sense evaluating some kind of second derivative of V. Okay, so we're evaluating the second derivative in two different ways, and we're taking the difference between these vectors that we're getting. One is along the curve C prime, one is along the curve C, and we're dividing that difference by this epsilon delta. Okay, and schematically, what that leaves us with is once we divide out this epsilon delta, we roughly have something like R times V. Okay, so very schematically, the difference, the second order change in V is very schematically, okay, the difference in the vectors is some Riemann tensor times the vector. Okay, so now the entire point that we'll argue is that difference in vectors, okay, is or this quantity that we're calculating, this R itself, okay, that coefficient of V, this is a measure of curvature. Okay, those coefficients that we had written down. Okay, this itself is a measure of curvature. Okay, and this measure of curvature is actually independent of the loop that we're using. Okay, it's independent of a particular loop. Okay, because in the end we're just taking the limit epsilon and delta go to 0. But even in the limit that epsilon and delta go to 0, this quantity is still well defined. Okay, and it doesn't depend on epsilon and delta. Okay, so this quantity is still well defined. Okay, you can think of it as roughly, I took this difference, it's small, it's proportional to this, I divide out by that size, and whatever I have left, that coefficient, that is really a measure of my curvature. Okay, and it's capturing how much those vectors have changed by parallel transport around different infinitesimal paths. Okay, and you could have either done it by calculating, the transport along two different paths, or I could have imagined transporting along a closed loop. Okay, it's really the same thing. Okay, you get exactly the same difference. Okay, in between the vectors. V naught, if I transported it along the closed loop, I would have got some V naught prime, and it would look exactly the same. Okay. Yeah, okay. Now, the fact that this is independent of the infinitesimal loop that you're using, the fact that this R is independent of the epsilons and deltas, okay, this tells you that R is a local property. Okay, it really doesn't depend on the loop that the particular loop that you're using. Okay, it depends on the direction, sure, but it doesn't depend on the size of the loop. Okay, so so really it is sort of a property associated with the point P itself. Okay, it's not a property of the manifold, I mean, which is spread out. It's associated with a point. Okay, the second thing is that R is independent of V also. Okay, it's independent of the vector components themselves. Okay, you see that it only depends, this R that we calculated only depends on the connection coefficient evaluated at P and its derivatives, okay, evaluated at P. So it doesn't really care about anything else. Okay, it doesn't care about which vector you use, which loop you used. So it's V independent, which means it's an intrinsic property of the manifold. It's not specific to any particular vector. Okay, it's some intrinsic property of the manifold which will tell you how all different vectors can transform under this parallel transport around a closed loop. Okay, so this R, these coefficients, R, mu, nu, rho, sigma, right now we don't know it's a tensor. Okay, these coefficients themselves define for you a notion of curvature. Okay, so now what we'll do is the claim is that when we put these coefficients as the coefficients of a tensor, okay, so we'll define a tensor called the Riemann tensor. Okay, we'll define it with these coefficients R, mu, nu, rho, sigma times partial x mu times dx nu, dx rho, dx sigma. Okay, we'll define this object as a tensor. Okay, it's not sufficient to just throw in something with indices and say that this is a tensor. It must also transform like a tensor. Okay, so that is the critical thing that we have to check. Okay, this defines a 1,3 tensor, but the non-trivial thing to show is that this R mu nu rho sigma, okay, that this coefficient transforms like a tensor under coordinate transformations. That is, supposing we now switch from an x coordinate basis to a y coordinate basis, these tensor coefficients, they must transform as a 1,3 tensor, and a 1,3 tensor with these coefficients transforms in this particular way. Okay, you can check this rule, right? But basically, when I switch over to, let's say, mu prime, rho prime, sigma prime indices, right, that they must appear kind of in the same way in. So this should appear as y mu prime, partial x mu, partial x nu, partial y nu prime, and so on. Okay, with the original R mu nu rho sigma. Okay, and here there's a sum over mu nu rho sigma, which is implicit. Okay, so this is the tensor transformation rule. So the non-trivial thing to do is to show that this object really transforms like a tensor. Okay, and it will transform like a tensor if these coefficients transform in this way under a coordinate transformation. How do I check how these coefficients transform? Well, you actually know the rule for how gammas transform. Okay, you know the rule for how gammas must transform for them to be valid connection coefficients. That is, if you use the transformation properties of gamma, gamma we've seen transforms partly like a tensor, but it also has this inhomogeneous part. Okay, as you've seen, this inhomogeneous part is pretty important, right? So gammas transform, they don't transform like tensors. But the remarkable thing is that when you stick gammas into this expression, okay, all those inhomogeneous pieces which all those inhomogeneous pieces together also conspire in such a way that the full R mu nu rho sigma still transforms like a tensor. Okay, the full R mu nu rho sigma will still transform like a tensor. That is kind of remarkable. Okay, this is the hard way to show it, but it's a very straightforward way. Okay, is you use the transformation properties of gamma. So you transform all the gammas inside the definition of R mu nu rho sigma and check that the coefficients R mu nu rho sigma transform like a tensor. Okay, this is the hard way, but it's a straightforward way. Okay, so you can do some work to show it. If you do, then it's obvious now that the Riemann tensor is a 1,3 type tensor. Okay, that is, and even though we found the expression for the Riemann tensor in a particular coordinate patch, right? We expressed it in terms of gammas. and their derivatives, and gammas are defined in a particular coordinate patch. But the object that we are looking at, the Riemann tensor itself, okay, itself is coordinate independent. It's an object that exists independently of any coordinate system. Okay, so even though we defined it in this approach to defining it, we used a particular coordinate patch. Okay, and the tensor itself, this Riemann tensor, is defined independently of any coordinate system that you use. Okay, just like any tensor field that you define in the manifold, okay, that tensor field is independent of any coordinate system that you use. Okay. Okay, so one really important word of warning, okay, especially if you've been using different textbooks to kind of follow up with this, is different textbooks use different conventions for the Riemann tensor, okay, and the ordering of the indices that you put into the Riemann tensor is a choice, okay, and it's important to remember what is the choice that you're making, okay, what is the choice that you're using. So when I write the Riemann tensor, okay, so this N stands for Nakahara, okay, so this is Nakahara's convention, okay, which is the discussion I'm following is roughly based on Nakahara now. So the Riemann tensor coefficients are written as mu nu rho sigma, okay, and then you think of it as this is a vector-like index, so expanded in a vector basis. These are dual vector indices, so they're expanded in a dual vector basis, okay. But the ordering of this nu rho sigma is very important because if you recall, this R mu nu rho sigma, right? This nu is the coefficient of the vector in the transformation, okay, in this difference when I expand it in terms of the original vector, this nu is the coefficient of that vector. Mu is the free index, that is mu is this index, it's the difference index, okay, it's the index of the vectors whose difference you're taking. And rho and sigma are indices of epsilon and delta, okay, that is there of the path that you're taking. Okay, so it's important to keep in mind what is the ordering, okay, of these indices. Okay, so we're defining it like this. We're defining it in this way. Okay, we're defining it like this. Okay, so with this particular ordering. If you use the textbook by Wald, okay, in Wald's textbook, Wald defines the Riemann tensor to be again the coefficient of some dx rho, dx sigma, dx nu, partial x mu. Okay, and the ordering of the indices is rho sigma are of the path, that is there of delta and epsilon. Nu is for the vector, and mu is associated with is the free index, okay, of the vectors that you're comparing. And moreover, okay, if I want to relate this, okay, rho sigma nu mu, okay, to the indices that we're using in Nakahara, the Wald rho sigma nu mu is minus r and mu, okay, so our mu appears first, our nu appears second, and our rho and sigma appear like this, but there's also an all-important minus sign, okay, in the definition of this r in Wald. Okay, it's just a peculiarity of how Wald is actually defining the Riemann tensor. Okay, but the physical object is still the same. You're just expressing it using sort of different components or different, well, the different ways to write down this same tensor. Okay. The good news if you're following Sean Carroll is that Nakahara's convention agrees with Sean Carroll, and we'll continue to use this convention, okay, in this course. Okay, if you're using Wald, use this dictionary, okay, to transform your Riemann tensor, okay, because that's the convention that I'll use in the problem sets and the answer. Okay, if you want to compare the expressions, you can look at these equations in Nakahara, in Carroll, and in Wald, okay, to compare them with each other. Nakahara and Carroll's expressions are identical. Wald, if you change the indices around carefully, and then you'll see that this is exactly the relationship between Wald's Riemann tensor and Nakahara or Carroll's Riemann tensor. Okay. Okay. So Yeah, let me just say this last thing and then we'll stop. Okay, so rather than having a single number now that quantifies the curvature at a point. Okay, so previously we saw this 1 by r square for a sphere, or 1 minus 1 by r1 r2 for the saddle point. Now we have a curvature tensor. Okay, we have a tensor rather than a number which quantifies the curvature. Okay, and if I want to specify that tensor, what you need is so for every choice of these indices, I will get a number, which means these indices take n values, where n is the dimension of the manifold. So there are n to the 4 numbers that need to be specified to specify the Riemann tensor. Okay, at a single point of the manifold, and that entire Riemann tensor tells you something about the curvature at that point on the manifold. Okay, but one important property that you have is, so if you remember, this was the epsilon index and this was the delta index. Okay, if I swap those indices, okay, if I swap so this is the epsilon index, this is the delta index. If I swap the indices, then what I'm essentially doing is I'm switching my path, okay, to this path. Okay, if I switch my path, then basically, so I'm switching what I'm calling C and what I'm calling C prime if I swap epsilon and delta, or if I swap the indices rho and sigma. So what that means is, instead of taking VC prime minus VC, I am now taking VC minus VC prime. Okay, and therefore the Riemann tensor picks up a minus sign under that swap of indices. Okay, so I have anti-symmetry in these bottom two indices because I'm basically taking I'm exchanging the path C prime and C. Okay, so the Riemann tensor doesn't have all independent entries. Okay, it has some anti-symmetry properties. Okay, so these two indices are anti-symmetric. So rather than having n to the 4, okay, mu and nu I can still choose in n ways. So I have n square values, but rho and sigma, okay, I have to choose them in such a way that rho and sigma, I can choose only NC2 of them. Okay, these are the number of ways I can choose them. I have to choose them to be different numbers. Okay, so out of the n dimensions or n values that rho and sigma can take, each one has to be different. So that's NC2. So I have n cube into n minus 1 by 2 numbers. Okay, these are needed to fully specify the curvature at a point. Okay, so instead of having one number now, we have a larger number of numbers. Okay, and in particular, this is a tensor. Okay, and it's a tensor that's anti-symmetric in the last two indices. Okay, so in the next class, what we'll do is we will explore more properties of this Riemann curvature tensor. Okay, maybe we'll also see another way in which we can much more easily show that it's a tensor. And now that we have this quantification of curvature, okay, this will be the final sort of mathematical ingredient that we'll need for manifolds before we can move to the general theory of relativity. Okay, yeah. So next class we'll just continue to develop this idea of curvature. Okay, I'll stop here for questions.
So can you explain once again that why r mu nu rho sigma is a local? Is it just because it is independent of vector v?
It's local because it's independent of epsilon and delta.
They are by definition infinitesimal.
No. So yeah, yes, it's true. By definition, they're infinitesimal. It's like saying f prime of x, right, is even though f prime of x you would say is, it's the limit of f of x plus epsilon minus f of x, right, as epsilon goes to 0. And you'd say really it depends on epsilon, right? So it isn't just non-local. But at the end, when you take the derivative, you're evaluating the derivative at a particular point. Okay, so you're associating that derivative with the point x. So it's the same thing here. We're taking a difference between two vectors. Okay, that difference is not, it's kind of like a second derivative. So it's not proportional to epsilon, but it's proportional to epsilon times delta, right? It's like taking the derivative in one direction and then taking the derivative in another direction. Okay, so it's like a second derivative. That's why I wrote it's like a second derivative here. We'll see that there's a more formal definition where you can think of, roughly speaking, taking the derivative in the epsilon direction, then taking it in the delta direction, versus taking the derivative in the epsilon, first in the delta direction and then the epsilon direction. The difference between these two operations, okay, is roughly speaking the Riemann tensor times, this acting on a vector, okay, is roughly the Riemann tensor times v.
Yeah. Okay.
Okay, and since it's a derivative, basically that's why you're associating it with the point at which you're taking that derivative, which is the point P. Other questions? Okay, if not, we'll stop here. So do review the discussion, okay, especially if you're not familiar with or not comfortable with index manipulation, get comfortable with it, okay. It's really important that you are very confident about manipulating indices, knowing not to use repeated indices. Again, right, it should only appear once as a lower index, one as an upper index, checking that the free indices match on both sides of an equation. All these kind of things should be very familiar to you. Okay. Toshif, you have a question?
Sir, yes, like I had a question regarding that Lagrangian of the earlier class.
Yeah.
Like, sir, when we are like using the arc length as the parameter, like isn't it obvious then then L will be equal to 1?
Yeah,
Like,
L will be equal to 1, and therefore dl ds will be 0.
yes. So why did you just say in the start that it is it is hand waving, but it is obvious that it will be 1?
So I didn't get it. Why is it obvious?
So like because S, like we started with the action, which was actually the path length. So S is integral ds. Now when we're using lambda as the arc length, then actually lambda is small s.
Is ds.
So it
right.
is, yeah. So it is integral root over of g. Yeah. ds.
This is the
Times
arc length.
ds. Yeah.
Times
So
ds.
this
Sorry.
thing is,
Yeah. This is 1 by definition.
yes, sir. So why isn't it obvious from here?
Yeah, I suppose it is. It's obvious that it has. Yeah, if you're using a if you're not using the arc length as a parameter, that would still be a valid parameterization for this action, except this would not be 1 in that case, right? Yeah, I suppose it is obvious, right? This is by definition the arc length, isn't it? No, sorry, this is by definition 1. This is the norm of the tangent vector to the curve. I guess the question is, how did we introduce this factor?
Yes. That is the Lagrangian. So like when lambda is s, it is 1.
Sorry, when lambda is?
Like when lambda is s, this is 1. Like when lambda is the arc length.
When lambda is s, this is 1. Yeah.
So it is always.
Yeah. Yeah, because I mean, for infinitesimal parts, it should still be true that these are the same. Right, and therefore this factor has to be 1. Yeah.
Sir, the overall variation will be 0, but that variation, I mean, delta S should be 0 on the action. So that delta will act separately on metric and x mu and x nu, because these are itself the function of lambda. So overall will be 0, but we will get an equation in between, I mean, the variation of these coordinates and metric, such that the overall variation should be 0. Like we can assume it 1 over 2 root f and then del f ds equal to 0.
So I'm not following what you're saying. So
If I assume this, the quantity inside under root, some function, so del s, the variation action will be, yes sir,
this, right?
del L over del X.
Yeah, the Euler-Lagrange equations.
Yes sir. So this L contains, I think, 3 parts, the metric and x mu x in. So we'll vary them separately and the overall will be 0. Like this.
No, L only depends on x and x dot. Right? I mean, x dependence is coming through the metric.
Yes sir.
So you only have to differentiate with respect to x and x dot like we did in class. I think the thing that is sort of I guess the thing that's sort of making it uncomfortable is that this x mu, see, the thing is that this metric is valid in any, this Lagrangian is valid in any parameterization. And we're not, you're completely free to choose the parameterization here. And of course, it's true that if you choose the parameter to be arc length, then this action becomes sort of trivial, right? And S basically is, yeah, so if I look at it this way, then what does it even mean to take the variation of S with respect to x mu if there is no Lagrangian, right? And I think the point is that you impose this condition that it's the parameter is the arc length by an extra Lagrange parameter. Sorry, you know, you're familiar from classical mechanics how to use Lagrange parameters for imposing constraints on a Lagrangian? Have you seen that before?
Yes, sir.
So, yeah. Okay, let me just review, some of these. I mean, this discussion is there in Blau. So let me just review that discussion and try to just do it a little clearly. Because the point is, if this and this are equivalent, why can't I treat the Lagrangian as trivial, right? And that obviously doesn't make sense. I still have to treat S as a function of these functions x mu. And what sense does it make to make lambda again a function of the x mu's, right? By making it arc length. Well, it's not a function of x mu. Yeah, I guess you're finding the equations of motion subject to the constraint that this entire thing is 1. That is, this quantity is 1. So that is the constraint that you have to impose. Yeah, very good. So I think if you do that, then you will get the geodesic equations with the affine parameterization. And that's why it's equivalent to using F. If you don't impose the constraint that this is 1 through the Lagrange multiplier, then yeah, okay, so the constraint is imposed not directly but through a Lagrange multiplier. Okay, so you don't really impose that this is 1. Okay, when you treat the action as a function of F. Okay, you do this, okay, you treat it as lambda, and then you impose something like this. I mean, I'm just guessing, okay, but maybe the exact form is different. So something like this, okay, so this is a Lagrange multiplier which enforces the condition that this is 1. So now I treat S as a function of X and alpha, okay, and so you see that we're not really imposing that this is, we're considering all possible X of lambda and all possible alpha of lambda. Okay, and we find the equation of motion for those. When you find the equation of motion of alpha, that will, in the equations of motion, you're setting this constraint. Okay, you're not setting it directly at the level of the Lagrangian itself. Okay, and so when you take the equations of motion, then you'll get some equation of motion for this. Okay, and you have to consider the Lagrange multiplier also there. I guess the other equation of motion will just solve for alpha. So this is really the only equation of motion. Okay, I have to check out to impose this Lagrange, this constraint, but I mean, basically the point is that you don't want to just directly set this to 1 in the Lagrangian itself, right? You want to impose that constraint through a Lagrange multiplier so that you get dynamical equations. By the way, since for those of you here, let me just tell you something interesting, right? D lambda. So it basically, there's one parameter that describes where you are, okay, and it follows some time-like curve, okay, and you extremize this to find basically the thing that extremizes the proper time of this particle, which is also the arc length along the curve. It turns out in string theory, okay, that you don't have a particle, but you rather have a string. Okay, so it's a sheet. It traces out a sheet like this in time. So there's some kind of measure of proper time along the particle, and there's sigma, which is a measure of the distance along the string itself. And therefore, you get an action for the string. Okay, this is called the string action. Okay, or the Nambu-Goto action, which is it sort of has a, so this parameter is, let's say, d tau or d sigma. So now there are two parameters, and instead of trying to extremize the length, okay, the thing that you're extremizing is the area of this world sheet. Okay, so let me see if I can write that. Yeah, so there are eta there's a GAB X partial. It's something like this. Okay, let me just. Okay, I don't remember the exact expression, but this is the area of the world sheet rather than the arc length. And if you extremize this, you get basically the equation of motion of a string. And you do something completely analogous to, like when we went from L to the square of L to get the action. You do something completely analogous in string theory, right? Which is you switch from this world sheet, which involves a square root, okay? And it turns out when you try to write down a quantum theory for this, it's very difficult to work with this kind of square root. Even the classical theory is very difficult to work with. And so what you do is you go to the square of this as the action, and that gives you something called the Polyakov action, okay, which is the analog of F, okay, which is something like this. So maybe I can just look this up and tell you what it is next time. Okay, but that's basically it. I mean, that's you know, any intro to string theory book will basically start with some action like this. Yeah, okay, so I think I can write it down. So there's a metric on the world sheet itself. Okay, so there's a metric on the sheet which depends on sigma and tau, and that metric I'll use here. Okay, and then there's this entire world sheet is embedded in some dimensions. Okay, and in string theory there's a prediction that you're in 10 dimensions. Okay, so well, in this bosonic string theory it's actually 26 dimensions, and so you write down some kind of action like this: x partial a partial b x g a b. Okay, and this a's and b's take values in sigma and tau. Okay, and then there's an x mu x nu, and that's the metric g mu nu of x. Okay, so x is a function of sigma and tau. Okay, it tells you the coordinate of a particular point on this world sheet. Okay, as it's embedded in this 26 dimensional spacetime, which is 25 plus 1, 25 spatial directions plus 1 time direction. Okay, and so there's a metric on, so this string is moving through a curved spacetime background, and this manifold of the string world sheet itself can be curved. Okay, and that curvature is encoded inside this GAB. Okay. Anyway, that's a longer story, but I basically wanted to point out that this is not a trivial. I mean, it's not just, you know, a one-time thing. Okay, it's useful to know this trick for this action and writing it using this constraint. So I'll try to set that as a homework problem. Okay, let's stop here since it's already 9. So I'll see you on Monday next week.
Thank you, sir.
Okay, see you. Bye.
Thank you.
Thank you, sir.
Hello.
Yeah.